tells you that you have a quartic polynomial. What does that mean? It's going to have degree 4, which means if you have it in polynomial form, not factored form, the highest power you'll see is 4. So based on our conclusions yesterday, if it's degree 4, not yesterday, you know what I mean, Wednesday, if it's degree 4, how many linear factors will there be when you factor it? 4. How many zeros? 4. Now remember, sometimes you have 4 zeros, but 2 of them could be the same, but you still count them separately. 1, 2, 3, 4. So how many zeros did I give you in this second, after I told you what its dimensions are? How many zeros did I give you? I gave you 4? Right. Even though I only wrote down 3 of them, -2, 2, and I, you know that for your non-real roots or zeros, roots is just another name for 0, you always have the non-real zeros and your irrational zeros always come in pairs. So even though we don't write it, the zeros are -2, 2, I, and -I. What's the purpose of my giving you this information here? F of 3 is -150. Yeah, this is a point on your graph, 3, -150, and you use that to find your value of A, your leading coefficient, which most of you left out on your quiz. You didn't find the value of A. So when I start this off, I do this type of thing. F of X equals, I just write it generally, A, whoops, A, and we know it would be A sub 4 because the leading term here would be a 4th degree, but you don't have to put the subscript in. And then I put 4 sets of parentheses like this, and I do X minus, X minus, X minus, X minus. And now I know I have 4 spots to fill in. The first spot is going to be a -2. I could pick any one of those numbers because this is all multiplication, so the order doesn't matter. Let me shut off Pandora so I'm not talking over music here. Okay. Shut off. Come on. There we go. So when I do X, take away a -2, that becomes what? X plus 2. And then I do X take away 2, that stays the same. And then I do X take away I. And then I do, oops, this is supposed to be a -I there. And then I do X take away a -I, which becomes X plus I. So what's nice about this factoring here is that these first 2 factors are conjugates of each other. So when you multiply them with FOIL, your middle term disappears. Makes it real easy. You're going to get the difference of perfect squares here. And when you multiply these 2, which are conjugates, you're going to get the sum of perfect squares. So this becomes A times X squared minus 4 times X squared plus 1. Now we've got to figure out what A is, and that's where this point comes in handy. So everywhere you see an X, you're going to replace it with the number 3. So everywhere I see an X here, I'm going to replace it with the number 3. So F of 3 equals A times 3 squared minus 4 times 3 squared plus 1. And it would be really nice if I knew what F of 3 is. I do know what F of 3 is. F of 3 is -150. That's the Y value when X is 3. So I replace F of 3 with -150. And now I have an equation. Once I evaluate each of those values there, I have an equation with one unknown, and I can solve it very easily. You could solve this way back in introductory algebra. A is equal to -3. So F of X is -3. That's my leading coefficient times X squared minus 4 times X squared plus 1. You could have left it all in completely factored form like the first sentence here if you wanted, the first equation. Now, what did I ask you to do here? Did I ask you to put it in polynomial form or factored form? Both. Okay, so to put it in polynomial form, This is factored form, and this first one up here, if you throw a -3 up here, that's also factored form. Either one of these is acceptable to me. To put it in polynomial form, you have to multiply these two first with FOIL, and you would get x to the 4th minus 3x squared minus 4. You use FOIL on that. And when you multiply that whole thing by a -3, you're going to get -3x to the 4th plus 9x squared plus 12. So that's your polynomial. This is in standard polynomial form where everything is terms. That means you have adding and subtraction. And here's your, up here is your factored form. So those are the two forms. And this is standard polynomial. So you have 3 problems under number 2 that you're expected to do. And if you can't do them, you should be seeing me, a tutor, or going to the math studio. Okay, that's what you need to complete in order to be ready for your next assessment on this material. Any questions on this particular problem right here? Where any of the information came from or how we got it? Because we're moving on to new stuff today, so I want you to make sure you understand this before we move on. Anything? Any way you can formulate any questions? Okay, well, let's hang on. Let's talk about this one first. Anything here at all? Yep, Alex? This one right here? Okay, because right up here in the actual information you're given, it's just like when we were doing lines and quadratics. You have, in order to get all of your equation filled in, you have to know a point that lies on your graph. And here's the point right here. When x is 3, the value of your function at 3, which we call our y value, is -150. So when I come down here, I put in -150 where I see y, and 3 where I have an x right here. And then now I can evaluate the actual number each of these parentheses are and then solve for A. Anything else? All right, so Brendan has a question on B. Okay, B says, I'm not going to do this, but says a quintic. What degree is quintic? 5th. So N is 5. And what's your question here? Okay, well, my guess is that you have to put, this is the point that you're given 0, 2. So just like you filled in 3, -150, you use that as your point once you get this in factored form. So try that, Brendan. Anything else? Okay, so let's take a look at, I also want to mention, I'm just going to throw this in. You had 2 or 3 homework problems last night. I was looking late last night, well, early last night, because I had to go to my neighbors to use the internet. I was looking at your progress with the homework, and both you and my next class. And at that point, at 7 o'clock, there wasn't too much progress. But you had several polynomial functions that were x to the 4th power. I think you had 2 of these. You know, they were really long, blah, 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 blah. And it says to use a graphing utility. So Reed had written me an email saying, you know, I got the first one. I put this into GeoGebra, and he found a 0 at -1. So he knew that x take away -1 becomes x plus 1. And he knew he got a cubic left in here, some cubic, because an x times an x cubed gives you an x to the 4th. And then he said, I don't know how to continue. The process just continually gets repeated. You keep reducing your polynomial that's there. So we started off with a 4th degree polynomial. We found 1 0, and now we have this cubic. So again, you put this cubic into GeoGebra or your calculator, and you find another 0. And lo and behold, you remember what that 0 was, the second 0? Read? Not a clue? Okay. The second 0 for this, well, the one he was looking at, the second 0 for this cubic also happened to be another -1. It went through the graph at -1. So now you have x plus 1 times x plus 1. So you do long division or synthetic division on that when you pull out an x plus 1, And then you'll have a quadratic left in here, and then you can do whatever you want. But I think with the one that was in the first one in the homework, I think this was like number 2 on your homework. They started you off really pretty quickly on that homework. And this is a quadratic, so you could use your quadratic formula on that. So you just continue the process. You find 1, 0 with some kind of graphing utility. You use long division to get your cubic. Then you do the same thing again, and you're going to get a quadratic. And then you can use, if you have a quadratic that's nice, you can either factor it or use a graphing utility. But this particular quadratic, if I recall, had non-real 0. So you couldn't look at a graph to get them. You had to use your quadratic formula. Okay, so maybe some of you didn't get all the way through that homework. So keep working on it, because it's a really good assessment for you to see if you have polynomials completed. Okay, so today we're going to start this new topic, and this finishes off chapter 3 for us. After we finish rational functions, we're going to take a step into exponential functions next week, and then a little bit of logarithms. Then we have Thanksgiving break, and we probably have an exam, I would think sometime soon after Thanksgiving, I think, right? Has anybody looked ahead? Okay. And then we just have a few classes after that left before the final. So pretty much once you have your material for test 3, you pretty much you'll be tested on just about every single thing you'll see on the final. Okay, so don't forget your projects are due next week, your GeoGebra projects. And I just want to point out something to you. When you put in your polynomial, your student ID, this is what happens a lot when students pass in their paper with their graphs. What's the problem with that? I can't read. I can't see what your polynomial is that you're graphing. So make sure you take this little arrow here and you scoot it over so I can see the full polynomial before you print it out, okay? I'll probably remind you again on Monday, because I know that sometimes we have a tendency as human beings to wait to a day or two before something's due to do it. So please, when you print this out, make sure at least one of the printouts, just one, has the full student ID polynomial, so I can actually see what your polynomial is that's being graphed. Because I actually do put them all in and check it, believe it or not. I know, it's kind of crazy, but I do. Okay, so rational function, I hope by now when you see rational, you think of the word ratio, and then you think of the operation division. So prior to today, we've looked at rational numbers, which we call fractions sometimes, but even whole numbers can be written, integers can be written as rational numbers by dividing them by 1 or making them into an equivalent form. So now we're looking at the ratio of two functions. So a function is expressed as p of x divided by q of x, where if you looked at p of x all by itself and q of x all by itself, they would both be polynomial functions, which you're very familiar with at this point. But when you divide them, you have to start being a little more careful, because number one, you now have a denominator, which you know could be a trouble spot in terms of your domain. So now we have to start thinking a little bit more carefully before we graph these functions. Okay, so here's an example of a rational function. Notice I put the numerator, which is just a quadratic trinomial. I put it in standard polynomial form, which means it's something plus something plus something. But yet I factored the denominator. Now, why, if you got a rational function, would you hope that someone was nice to you and actually factored the denominator for you? Why would you hope that they had it all factored? Right, then you can look at the denominator and say, hey, I know what values of x is going to make that denominator 0 just from looking at it, because it's in factored form. So one of our concerns here is right here. The polynomial in the denominator, whatever that polynomial is, cannot be equal to 0. So whenever we determine what values of x will make a polynomial equal to 0, we have to factor it. And it's already done for you. So we have to say to ourselves, when does this polynomial equals 0. And again, it's the same strategy we learned a long time ago when we learned how to solve quadratics with the zero product principle. You take each factor, you set it equal to 0. The first one's already done for you. The second factor, when you set it equal to 0, will give you x equals 4. And the third factor, when you set it equal to 0, will be at -2. So if we were graphing this on a real number line, and remember, when we end up graphing this polynomial function, this rational function, the x-axis is like our real number line that we're used to putting open circles and closed circles on. So this is actually a beginning to help you think about what's happening to this particular graph. So at x equals 0, I have a big hole. Can't include 0. At 4, I have another big hole. Can't include 4. And at -2, I have an open circle. So my domain is all numbers to the left of -2, but not including -2. All numbers between -2 and 0, with -2 and 0 not being included. 0 and 4, between 0 and 4, not including 0 and 4, and then 4 all the way out to positive infinity. So that's how we represent it. Like when we first started talking about domains way back in September, it's actually, this is the one time when it's a lot easier to use set builder notation to represent the domain than it is interval. This is a pain in the butt to do with interval notation. We'll do it both ways. But here, set builder is much easier. So if we use set builder notation to represent the domain, and remember, the domain isn't the excluded values. The domain is the entire set of values that actually work. So the domain for f in set builder notation is the set of all x except x cannot be, and then you just list them, -2, 0, 4, and then close with your little profile, your braces. That's pretty easy to do. If you use interval notation, which you know you're going to have to do on my math lab, it's a little more tedious, but you've had a lot of practice. You know you go from -infinity to -2, and you have parentheses on both of those. Then you union it with the set from -2 to 0. Again, all parentheses, because we're not including any of these numbers. You union that with the set from 0, the interval, the set of numbers from 0 to 4. And then finally, 4 to positive infinity. Notice you've got 1, 2, 3, 4 segments here that you've broken your real number line up into. So you have to have 4 sets of numbers in your interval. That makes sense when you look at the picture and you look at your interval notation. So the first thing we have to worry about with rational functions is what values of x will make the polynomial in my denominator equal to 0. And some really interesting things will happen when we graph these functions right around these numbers. Some really interesting stuff goes on. You might say, oh boy, interesting. If she says it's interesting, it's going to be a pain in the butt, right? But it's really fun stuff once you get the hang of it. You know, you start graphing these unbelievable things that if I just gave you like the graphs now and said, you're going to learn how to graph this, you'd say, no way. But it really is fun. All right, so that's the domain of a rational function. Any questions on how we find the domain or how we can represent it? Anything at all? Okay, Andre's sleeping, so he doesn't have any questions. This is boring for you, huh, Andre? You know all this stuff, huh? Oh, I'm sorry.
Obviously, the denominator is not like
yeah, yeah, I've already factored it for you. So if you had to factor it, you know how to find zeros now, either with a calculator or a utility, and start factoring it. Because this would be a cubic right here. This is degree 3, because you have 1 for each of these, right? So this, if I multiplied this all out, I'd get an x cubed as my first term. So you now can factor things you never could factor before, unfortunately, right? So now you have to do it. All right. So number 2 is what we just did. I already did number 2 for you. All right. So we're going to start with the most basic rational function, And every other case we've looked at, y equals f of x equals x, y equals x, the identity function, f of x equals x squared, our parabola, f of x equals x cubed, our cubic function, those are all called parent functions, right? This is our parent function for rational functions. It doesn't get any simpler than 1 divided by x. That's our parent function for our whole set of rational functions. So if we were going to do transformations, this would be our basic function we would start with. So this is our parent function. Does anybody else know what name we would give to this function from looking at what it is, 1 divided by x? Another name for it? What happens if you have an x and then you say 1 divided by that number? What's your result? For any number you pick, what's going to happen to the original number once you do this, apply this function to it? There's a relationship between, what is it? It's a quotient, yep, 1 divided by x is a quotient, but it's a very special quotient. So Karen, give me a number for x, any number you want. Pick your favorite number. 5. So if x is 5, what's my output? What is it? So when x is 5, oh, that's bad. Coleman? Oh, I can't throw with my left hand. So when x is 5, my y value is 1/5. Close, it definitely is an inverse, a specific inverse. Keep going, give me a favorite number, Reed. 8, what's my output? 1/8. Reciprocal, right? Whatever I put in here, what's my result? The reciprocal. What if I put a fraction in, like 1/100th? And I divide 1 divided by 1/100th. Oh my God, I have to remember how to do fractions, dividing by fractions. That's 1 times 100 over 1, which is what? 100. So my result is the reciprocal of whatever my input in is. So this parent function is called the reciprocal function because it just takes the reciprocal of whatever x is. So let's take a look at the domain, because we always have to be concerned about the domain with rational functions. So what's the domain of this function? So I'm asking you the question, what's the domain, not what's the excluded value, even though that's what this says. What's the domain? If you were to write out the domain, what would you say? Andre? All real numbers, the set of all real numbers except 0. Boom, you're done. 0's excluded, not allowed into the door. Okay, the bouncer's there. Interval notation. There we go in interval notation. So 0's excluded, it's not allowed into the club. So otherwise, we're free to put any number in on the whole entire real number line and just flip it around, take its reciprocal, and we're set. So we're going to fill in the value of tables here to see what happens, and this is now where we're going, folks. We know 0 can't be included. So notice how the y-axis here is a solid line. This solid line that we call the y-axis cannot be part of our graph anymore because 0 is not allowed in the club. So what we do is we make that a dotted line to say, well, it's certainly not part of our graph, but it's going to help us draw our graph. So for right now, I'm just going to put a vertical dotted line to remind myself that there's no way that my graph can be on this line because x can never be a 0. There can't be any point on your y-axis ever. Okay, so that's where I start. And now I say, well, if I can't be 0, what happens when I'm really, really close to 0? And notice you can be really close to 0 if you're from one side of the family, the positive side of 0, or from the negative side. Now you can determine which of your parents is the positive side and the negative side, okay? But anyway, or if you're married, the in-laws, right? So you have, you're approaching this 0. You're allowed to be any number but 0. So you're saying, what happens to my value of my function as I get really, really close to 0? From the positive side of 0 and from the negative side of 0. So let's take a look. We can do this because we all know how to take reciprocals pretty easily. So we're going to now take a look at x values, and this is the language that we use. This is brand new language for you. As we approach 0 from the right, as we approach 0 from the right. So I'm going to be out here on my x-axis, and I'm going to take a bunch of numbers and get really close to 0. So notice I didn't go too far out. I started with the number 1. So what's the reciprocal of 1? Reciprocal of 1 is 1. 1 divided by 1. 1 over 1 is 1. What's the reciprocal of 1/2? Yep, because a half is 1/2, right? And when you flip 1/2 around, you get 2. So it's easier if you put all of these decimals into fraction form, because when we think about making reciprocals, we think about just inverting our fractions. So it's much easier to put those decimal values into fraction form like that. And now when I take f of 1/10, f of 1/10, what do I get? 10. When I take f of 100th, what do I get? 100. When I flip it, take the reciprocal, and then f of 1/1000 is 1,000. So if I try to graph that, I'm not going to get very far on my graph here, because look, at 1, I'm at 1. And if I go halfway between 0 and 1 at a half right here, I'm up to 2 already. If I go a tenth of the way, I can't even do that with this pen, right? But I'm really close in here. A tenth of the way, I'm up to 10. If I go 100th of the way, I'm off the screen. And I go 1,000th to the right of 0, I'm up on the ceiling at 1,000. So as I start to draw this graph, as x gets really, really close to 0, what's happening to the value of my function? It's increasing, I agree. What else? The value of my function is f of x. So as x gets really close to 0 from the right, look at your table. What's happening to this value? Is it getting close to 0? It's getting really big, right? And it's getting really big fast. It's blowing up. It's going towards positive infinity. But it's going to hug as close as you can possibly get. Now you're going from a king bed to a queen bed to a single bed and maybe a little futon. There's a new name for those now, Japanese name for the little portable futons. You're getting really close to that y-axis, but you'll never be on that y-axis because x can never be 0. What about from the other side? Now, does that make sense to you that all of these have to be positive values? Because 1 divided by x, your numerator is positive, and all your x's are positive if you're on the right side, right? Now, let's go from the other side. But let's fill this in. As the x values approach 0, from the right, the values of my function approach positive infinity. So how do we write that sentence with mathematical symbols? We say as x approaches 0, and this little plus sign in the right-hand corner where you usually write your exponents, that tells you you're coming into 0 from your right-hand side on your graph. And the value of your function goes to 0. I mean infinity. All right, so now we're going to take values that are from the left-hand side of 0. So what are going to be, can you tell me something about the sign of all my outputs now if all my x's go in as negative? They're coming out negative because if I have 1 divided by any negative number, it's going to be negative. So what's f of -1 going to be? -1. What's f of -1/2 going to be? -2. F of -1/10? -10. F of -1/100th? -100, and then -1,000. So now if I go down in my graph, and that's all I'm interested in here, if I'm at -1, My function's value is -1. If I'm at -0.5, I'm at -2. If I'm at -10, I'm really close at negative. If I'm at -1/10, I'm really close to that y-axis. I'm at -10, and it has very similar behavior to the other side. But now I'm in the negative realm. So what happens to the sign of my function when I cross over from the left-hand side to the right-hand side? What happens to the sign of my function? It switches, right? It crosses. Even though when we were doing polynomial functions and we had an odd multiplicity, remember, we went straight through the x-axis and our function changed sign. Even though we're not crossing the x-axis here because we can't cross the x-axis because we've got an excluded value at 0. Notice our function changes sign as we take the smallest teeny baby step from the left-hand side to the right-hand side of 0. And I just want to point out something to you. Look at the denominator here. F of x equals 1 over x. What's the exponent on this x? 1. So that has odd multiplicity. So you should expect that at that point that makes that denominator 0, your function should actually change sign from one side of that number to the other side. You'll be below the x-axis to above the x-axis or vice versa because you have odd multiplicity right there. All right, this vertical line, and remember all vertical lines have this form, x equals some constant. This vertical line that goes through 0, which is the equation for a y-axis, is called a vertical asymptote. All right, vertical asymptote. And it's not part of your graph, but you put it in as a dotted line because it helps you draw the graph. The purpose is to help you sketch the graph. Okay, so we're not talking about end behavior here. We're talking about as we approach a very specific number that makes your domain undefined. So now let's talk about the rest of this function. What happens to the rest of this function as x now starts traveling out towards positive infinity and as x starts traveling out towards negative infinity? What happens to the value of my function? So that's where we're going next. But before we get there, we want to ask the question, do we have any intercepts going on here? Because that helps us. So let's see. We know what happens next near 0, so let's investigate other characteristics of the graph. Does f of x equal 1 over x have any x or y-intercepts? Well, first of all, to find your y-intercept, you let x equal 0. That's not allowed, so there's definitely no y-intercepts. To get x-intercepts, you say, when is the value of my function equal to 0? Well, f of x is 1 over x. Can 1 over x ever equal 0? No, because look, the only time a fraction can equal 0 is when your numerator equals 0. Your numerator is a constant. It's 1. So you're not going to have any x-intercept either. So now, just to finish off the sketch of this function, all we have to do is say, what happens to the ends? What's the end behavior look like? So we know, I'm going to go back to my first page right here. I've got my values of my function as I get close to 0. Now what happens as I start putting in big numbers? What happens if x is 5? What's going to be the value of my function? 1/5. So at 5, I'm like 1/5 of the way up. What happens at 10? It's 1/10. Oh my God, I don't even know if I can put that in there. Oh, it looks like I'm on the x-axis. What happens as I go out to 1,000? How far above the x-axis am I? 1/1000th. What if I'm 1 million? I'm out there at 1 million. How far above the x-axis am I? 1/1,000,000th high. Yeah. So, you know, my pen, the thickness of my pen is going to make it look like it's on the x-axis. So my end behavior says, as x gets really, really large, of course, my reciprocal is going to get really small because they have an inverse relationship, as I think either Boo or Morgan mentioned earlier. So as x gets really, really big, what's the value of my function approach? look at my value of my function here. Don't get confused. What's this value getting really, really close to? 0. It's getting close to the x-axis where y is 0. Your output is 0. And similarly, on the other side, we know we have exactly the same behavior. We call this horizontal line, which is your x-axis, right, which is y equals 0. That's your x-axis. That's the equation for your x-axis. We call this the horizontal asymptote. So again, we put in this particular case, it's just used to help us graph the end behavior. So here, the value of your function is approaching 0 as x approaches infinity in both directions. So that how we write that is how we usually write it, as x approaches infinity, the value of my function approaches 0. It gets very close to the x-axis. As x approaches negative infinity, the value of my function also approaches 0. So the graph of your reciprocal function looks exactly like what we just saw on the other page, and I'll draw it for you. It looks something like this. With dotted straight lines for each of your axes here. And that's your reciprocal function. That's what it looks like. Notice, what kind of symmetry does it have? F of x equals 1 over x. What kind of symmetry? Origin symmetry, odd symmetry, because f of x, the opposite of f of x, equals f of the opposite of x. If I put, here's f of x, there's f of x, I put a minus sign out there. And now to evaluate f of negative x, I put a negative x in there, and this is what I get. They're equal as origin symmetry. If I put a 1 in here, I get 1. If I put a negative 1 in here, I get the opposite of 1, negative 1. So this definitely has origin symmetry, odd symmetry. Okay. So we got one more to look at, and then you're going to have the whole rest of the class to draw these folks. Here's another parent function, 1 over x squared. So right away you look at this. What do you think is going to be the difference between these two functions? It's going to have even symmetry, absolutely, because f of x is definitely going to equal f of negative x, because f of x is 1 over x squared, and when I put negative x in and square it, I get exactly the same thing. So it's definitely going to have even symmetry, which tells you that whenever you graph this, it's going to have a mirror reflection over the y-axis. So that's very different. Okay. What about the domain? Is that different? No, the domain's exactly the same. X squared is in the denominator. X squared cannot equal 0, so x cannot equal 0. So the domain here is exactly the same. It's a set of all x, except x can't be 0. So now we want to describe what happens as we get really close to 0. So first of all, I go down and I put a dotted line where my y-axis used to be. So it's no longer a solid y-axis. I can never have a value of x that will equal, yep.
Do you have to do that like on?
Yes. Yes. Yep. That was clear, right, Trevor? Okay. Use arrow notation to describe the behavior of f of x near this excluded value. What do I mean by that? What do I mean? Use arrow notation to describe the behavior of the function near the excluded value. First of all, what's the excluded value? 0. So I want to know what happens to the value of my function as x approaches 0 from the right and as x approaches 0 from the left. So in your mind, think about this for just 1 second. If you put in values of x as it gets really close to 0 and take their reciprocal, now you're squaring it and then taking its reciprocal. Oh my God, it's going to blow up even faster. Well, 1 stays 1 when you square 1. But think about 1/2. If you do f of 1/2, you get, instead of 2, you get 1 over 1/2 squared, which is 1 over 1/4, which is 4. So now at a half, you're up here at 4. Look at how quickly you're climbing that y-axis and hugging it. So you're continually to get closer and closer and closer. You're blowing up towards infinity. The value of your function is approaching infinity. It's getting quick very quickly. Now, here's the only part you have. Here's where the part changes. If x is positive or negative, if x is positive or negative, what's the value of your function going to be? Always positive, because if you square a negative number, you get positive. So guess what? We just found out, Coleman told us this has even symmetry. So it's going to look exactly the same on the other side. So whether x approaches 0 from the left or right, my function is quickly moving towards infinity. It's increasing without bound. All right. What about the end behavior? The end behavior says what happens to my function as x doesn't approach a specific value like it does with the vertical asymptote, but as x goes towards positive infinity and negative. What's going to happen to the value of f of x? As I get really, really big numbers like 100, and I do 1 over 100 square, it's going to definitely approach 0, both directions. And everything is positive, so we're getting closer and closer and closer to the x-axis. So that's your horizontal asymptote. So this definitely has even symmetry. We've already confirmed it. And there's the graph of 1 over x squared. So all you're going to do for your activities now is you're going to play with transformations of these two functions. You might be shifting them up. You might be moving them left or right. So for the whole rest of the class, you're just playing with transformations of these two. Trevor? Sure. We have no x or y intercepts, right? What's the equation of the horizontal asymptote? It's your y-axis, your x-axis, so it's y equals 0. Okay. So start working on, yeah, Coleman, did you have a question? Okay. Start working on your activities, and I'll help you as needed.